Hello, everyone. My name is Alan Wadsworth. I'm the Business Development Manager here at Keysight Technologies for Precision and Power Products. And I'm going to be the, I guess you'd say, lecturer today for this first webinar on our series of power webinars. It's DC and AC Power Fundamentals. So let's go ahead and get started. So here's the agenda I want to cover today. So I'm going to start off first going over some power basic stuff. I mean, there's going to be some equations and stuff thrown in here, but again, I just want to make sure that people have a good kind of theoretical understanding of some of the basics of power. And then next section, we're going to talk about AC power, sinusoidal waveforms, phase difference between, say, current voltage, what that means, things like that. And then I'm going to talk next about power transmission, basically talking about AC power transmission, three-phase stuff. Why do we do AC, why three-phase, those type of topics. And then the next section is to be devoted to power conversion. In other words, converting power from different forms, AC to DC, DC to AC, things like that. Why do we do it, and how is each used? And then lastly, I'll give you a summary and some additional resources if you'd like to learn more about anything that I talk about today. So this first section here is, of course, going to be power basics. And again, it does cover some really basic topics, and hopefully for most of you or all of you, it's just kind of a quick review. But again, I just want to make sure that everybody has a good understanding of this stuff before we move on to the more advanced topics. I'm going to start off by doing a quick review of work and power. And again, hopefully this is a quick review for everybody. So again, starting off the concept of work, again, in physics, that's defined as the action of a force on a particle over some distance, moving it. And it's defined by a vector equation, even though, of course, work itself is a scalar quantity. Again, if you take a charged particle and move it through an electric field in space, we know that the components acting on it, again, do require some work to be done. So we can define the electric potential difference between like 2 points A and B using the following equation. But again, since we really in electronics obviously want to work with the concept of potential at a point in space, well, how do we do that? Well, what we can do is we can take point A and say it's infinitely far away, and define it as 0 volts, which then reduces this equation to just the familiar voltage is work divided by the charge. And again, kind of understanding the work performed on something is less interesting maybe than understanding the rate at which the work is taking place, which is power. So again, the average power delivered by a system is simply given by total work divided by total time, right? But if we're talking again about electronics, I want to look at that voltages, things like that. We know that work and acting on a particle in an electric field is going to be the voltage times the charge. So that gives us that if we want to do the instantaneous power, it's a change in work over change in time, which we can rewrite as V times delta Q over delta T, or simply voltage times current. But again, it's the familiar equation for power in electronics. Again, hopefully this is just a real quick review for everybody. I'm going to do a real quick review of resistance, resistivity, and Ohm's law. So again, if we apply a voltage across two similarly shaped, say, rods of maybe whatever, copper and carbon, you'd obviously get very different resulting currents. And the property that you're observing there or that comes into play, obviously, is the resistance. And again, you define resistance between two terminals of a material by applying a potential voltage across those terminals, measuring the current, and dividing by the current. So again, R equals V over I. But again, a lot of times the resistance of a particular sample, because it depends on its dimensions, that's not necessarily so interesting. We often prefer to look at the resistivity shown by the symbol rho here in this equation, because it's independent of the sample size, and again, it's easy to calculate the resistivity from a resistance measurement if we know the cross-sectional area and its length. So again, now if we apply a variable voltage across the terminals of many, not all necessary materials, but certainly for all metallic conductors, we actually see a straight line. And this important result is, of course, known as Ohm's law. Now, it is important to note, though, that the Ohm's law does depend actually on the sample remaining at a constant temperature while we're making the measurement, because resistance actually can vary as a function of temperature. And the reason I mention this is because the power going through a resistor is obviously voltage times current. And again, you can, using Ohm's law, you can re-express that as either V squared over R or I squared R. But it is important to keep in mind, especially if you are measuring resistance or resistivity normally of a material that's very, very small, that it could be varying, it could be heating up. So you have to be very careful when you're applying voltage and current not to get too much heating to actually change the value that you're measuring. So from the equations shown on the previous slide, we know how to calculate the power dissipated if we apply a DC voltage to a resistor. But what about the case of a time-varying waveform? Well, if the waveform is periodic, then we can still calculate the average power dissipated over time, right, by calculating the power dissipated over one period and dividing by the period. But therefore, an interesting question to ask is, what is the equivalent DC voltage or current that we would have to apply to achieve the same amount of power dissipation? So obviously, the calculation of this equivalent DC value depends on the characteristics of the periodic waveform. But fortunately for us, most of the time in electrical engineering, we're dealing with sinusoidal waveforms, and that makes the calculation of this value much easier. So basically, we use our fundamental equation of power is equal to V squared over R, and then we just have to calculate the average value over one period. And again, for the sinusoidal case shown here, you end up with the equation shown in the lower right, which is basically a fairly simple integral. So taking the equation from the previous page and using a simple trigonometric identity, we can rewrite the equation or integral we just had as shown here. So we've eliminated the sine squared term. And then we can solve this pretty quickly and find out that the average power is going to be V sub 0 squared over RT, and the integral evaluated in these two limits shown there. And that works out, if you do the math, to the final result that we have the average power is equal to the amplitude of our sinusoidal, V sub 0 squared over 2R, or we can also write that as the amplitude over the square root of 2 squared over R. Well, what does that mean? Well, basically, it gives us a really convenient result that for the case of sinusoidal waveforms, we can compute their equivalent DC values simply by dividing their amplitude by the square root of 2. And again, this is usually referred to as the root mean square value of the waveform and has a subscript notation RMS as shown in this equation. Now, I do want to emphasize one thing, and that this convenient result only works for sinusoidal waveforms. And again, for other types of periodic waveforms, you would need to integrate them over one period and divide by the period in order to determine their DC value. Or I guess another way, if you had periodic waveforms, you could, I suppose, also represent them as their Fourier components, which are sinusoidal, of course, and divide those by the square root of 2. Probably only have to do the first few of those, and you could get a pretty good idea of the DC value. But in any case, I just want to emphasize that this RMS rule of dividing by the square root of 2 is specifically for the case of sinusoidal waveforms. So in AC circuits, we're applying some sort of sinusoidal stimulus to the circuit. And of course, the voltage and current waveforms are both sinusoidal with constantly varying amplitudes. Now, the total power dissipated is still equal to the product of voltage and current. In other words, power is equal to V times I. However, this value will, of course, vary over time. Now, maximum power dissipation will occur when the voltage and current waveforms are completely aligned with no phase difference, because their peaks and zero crossings are occurring at the same time. Now, if this condition is met, the voltage and current waveforms are said to be in phase. And the phase relationship between voltage and current is determined by the circuit impedance, of course, which is in general a complex quantity. Now, impedance can be viewed as a triangle in the complex plane where the resistive component corresponds to the x-axis and the reactive component corresponds to the y-axis, as shown in this slide. Now, of course, impedance is a complex number represented as the vector sum of its resistive and reactive components. It has both a magnitude z and a phase angle theta, and we can use basic trigonometry to calculate the relationships between resistance, reactance, and, of course, total impedance. Now, remember that R does not depend on frequency, but the reactive portion of impedance is frequency dependent. So, of course, its value and the value of theta will vary with frequency. So we can take the impedance triangle shown on the previous slide and use it to calculate the various components of power using Ohm's law for a DC circuit. In other words, P equals I squared R. And this gives us the power triangle shown on this slide. Now, real power, which is also known as active or true power, is the power consumed by the resistive elements of a circuit, and it's measured in watts. And again, the resistive elements do not have any reactive component to them, so all the power they dissipate is converted to heat, light, and/or work. Now, we also have the reactive power component shown there, which is measured in volt-amps reactive, and the apparent power, which is measured in volt-amps. They're also, of course, important aspects of a circuit because in order for a circuit to function, you still have to apply enough apparent power to it to get it to work, even though it may only be dissipating, or it is only dissipating, the real power shown there, given by what's being dissipated by the true non-reactive elements, and power in watts, in other words. And I think on the next slide, this will become a little more clear. Virtually all practical circuits contain resistive, capacitive, and inductive elements in some combination. And we also know from basic circuit theory that of these elements, only the resistive elements dissipate net power. Of course, the capacitive and inductive components store energy, but at least for ideal elements, that energy shouldn't be dissipated and can be recovered. But again, for the circuit to function, enough power must be supplied to the circuit to satisfy both the resistive and reactive components. And for me, at least, this gets to the essence of understanding what is meant by real versus apparent power. Now, an important term to understand, of course, is the power factor. Now, in mathematical terms, the power factor is the ratio of the real power dissipated by a load divided by the apparent power going into that load. So, of course, power factor is dimensionless with values ranging from 1 to -1. A negative power factor occurs, by the way, when the circuit or device that is normally the load generates power back to the source. But again, conceptually, you can just think of the power factor as the amount of useful work generated from the apparent power applied to a circuit or load. So this completes the power basics section, and here's the key takeaways I'd like you to remember from this. So again, RMS values are a way to express periodic waveform power in an equivalent DC format. And this is easy to do for sinusoidal waveforms because we can simply divide their amplitude by square root of 2. But again, remember that this only works for sinusoidal waveforms. So the second point, of course, is that circuits typically contain both real and reactive elements. And of course, only the real elements consume actual power in watts. But you do need to apply total apparent power, volt-amps, to a circuit to get it to function. And again, you can think about impedance in terms, and power actually, in terms of a triangle, with the real portion represented by the x-axis and the imaginary or reactive portion represented by the y-axis. This takes us now into section 2, where we're going to be talking about many aspects of AC power. So we're going to look at the calculation of AC power. We're going to start off by examining the case where voltage and current are both sinusoidal waveforms at the same frequency. And of course, in the general case, we have to consider the effect of a phase difference, theta, between these two waveforms, which is as shown in this slide. Now, we can describe these waveforms using the equation shown in the lower left. And again, since power is the product of voltage and current, we can write the power equation as shown in the lower right. The equation from the previous slide isn't all that useful in its current format, so we're going to use a couple of trigonometric identities to modify it. So using the trigonometric identities shown here allows me to rewrite the equation as the difference of two cosines. And notice also I've eliminated the omega t term from at least one of those terms in the cosine, which is important. I'll show you in a second. any case, I do also know that I have my equations for RMS values, which is V0 over the square root of 2, I0 over the square root of 2. And that allows me to rewrite this equation again as the instantaneous power is the product of the two RMS values times the cosine of theta minus the cosine of 2 omega t plus theta. So again, the first component of this is obviously a constant. It only depends, of course, on the RMS values and the value of theta. And the second component is time dependent, and the frequency is twice that of the voltage and current waveforms. So, of course, the instantaneous power does vary over time. It's difficult to measure and not necessarily all that useful. It's actually much more useful to think about the average power, which, of course, we get from averaging this equation over one or more periods. Now, remember, of course, the average value of any sinusoid is 0 when you calculate it over one or more periods. So we can see that basically the average value of this is going to just reduce to the equation shown here at the bottom, which is the average power is the product of the two RMS values times the cosine of the phase angle between them. And of course, notice also that if the current and voltage are completely in phase, that is theta is 0, then the average power simply simplifies, I should say, down to the product of the RMS values of the voltage and current waveforms. So for these next 3 slides, I want to look at a little more detail AC power through a resistor, inductor, and capacitor. Look at the waveforms. So this first case here is AC power through a resistor, which of course is simple to analyze since there is no phase difference between the current and voltage waveforms. And again, the waveforms have the format shown in this slide. And again, since the voltage and current waveforms always have the same sign, either being both positive or both negative, again, resistors can only generate real power. In the inductor case, the current lags the voltage by pi over 2 radians, or 90 degrees. And the voltage, current, and power waveforms have the form shown on this slide. So again, although the inductor generates both the real and reactive power, over an entire period, they exactly balance out so that there's no, of course, net power dissipation. Now, in the inductor case, we can see that maximum real power dissipation occurs at 3 pi over 4 and 7 pi over 4 radians, and maximum reactive power dissipation occurs at pi over 4 and 5 pi over 4 radians. And finally, we have the AC power through a capacitor. Now, in the capacitor case, the current leads the voltage by pi over 2 radians, or 90 degrees. And the voltage, current, and power waveforms, of course, have the form shown on this slide. Now, as in the case of the inductor, the capacitor generates both real and reactive power. But again, over an entire period, they exactly balance out. So again, there's no net power dissipation here either. Now, in the capacitor case, we can see that maximum real power dissipation occurs at pi over 4 and 5 pi over 4 radians, and maximum reactive power dissipation occurs at 3 pi over 4 and 7 pi over 4 radians. So this finishes the section on just simple AC power. So here are the key things I'd like you to take away. So again, in general, AC sinusoidal voltage and current waveforms, of course, are not in phase, but are separated through some phase angle theta. Now, instantaneous power, of course, dissipated by two sinusoidal voltage and current waveforms does vary over time. But if you just look at the average power, that's simply equal to the product of the voltage and current RMS values times the cosine of their phase angle. And again, of course, since voltage and current flowing through a resistor are always in phase, that is theta 0, resistor can only generate real power. And the voltage and currents flowing through inductors and capacitors are always out of phase by, of course, a fixed amount. And for sinusoidal waveforms, the power dissipated by either element over one period averages out exactly to 0, which is, of course, you'd expect. This takes us now into section 3 of the webinar, which is all about power transmission. I think everyone knows, of course, that we transmit power in general by AC waveforms. And I don't know if you ever thought about the reasons why. It's not fundamentally that you couldn't necessarily say transmit power by a DC, but of course, we want to transmit power to be efficient at high voltages, which means we have to step it up for transmission and step it down when it comes into your business or home or whatever. And the primary reason that power transmission uses AC rather than DC voltages and currents basically is the relative ease by which you can step AC voltages up and down using transformers. So it's actually worthwhile to spend a little bit of time understanding some transformer basics. So what's a transformer? A transformer is an electronic component composed of two or more coils of wire wrapped around a ferroelectric material that transfers electrical energy by an alternating magnetic field. So again, transformers utilize Faraday's law of induction to convert electrical energy, again, usually voltage, from one value to another. But again, it's important to understand that transformers require an alternating magnetic field in order to function, so they can't operate on DC electric voltages and currents. Again, that's the reason why we generally use AC. So a simple single-phase transformer consists of two sets of wires wound around opposite ends of a magnetic core, as shown in this slide. And again, we denote one side as the primary winding, and it's usually the side that supplies power, usually at the higher voltage. We denote the other side as the secondary winding. It's usually the side that receives the power, and hence it's at a lower voltage. And again, for practical reasons relating to the magnetic flux and losses within the core, the transformer core generally consists of a bunch of plates rather than one solid mass. Now, an AC voltage applied to the primary input terminals creates magnetic flux that circulates through the transformer's core. The magnetic flux traveling through the secondary winding induces an AC voltage at the secondary output terminals. And since there's a direct linear relationship between the number of coils in the primary and secondary terminals and the primary and secondary voltages, of course, it's easy to control the ratio between them. And again, another nice feature, of course, of transformers is that the primary voltage and secondary voltage exist in complete electrical isolation from one another. I want to touch on the basic transformer equations here. But before I do that, I just want to mention that there's kind of three types of transformers. So again, if the purpose of the transformer is to increase the primary voltage, in other words, VP is less than VS, then it's known as a step-up transformer. And of course, conversely, if the purpose of the transformer is to decrease the primary voltage, in other words, VP greater than VS, then it's known as a step-down transformer. And if the purpose of the transformer is just to provide electrical isolation, then it's designed to ensure that VP equals VS. In other words, it's a one-to-one ratio. Now, assuming an ideal transformer and zero phase difference between the primary and secondary coils, then the transformer turns ratio formula determines the relationship between the primary and secondary voltages, as shown here on this slide. Now, it gives an example. Suppose we have a turns ratio of n equals 4, and we apply a voltage of 120 volts to the primary coil, VP. We can then easily determine the voltage at the secondary coil to be 30 volts. So I explained why we transmit power using AC waveforms, but I didn't really talk much about the details of how that's done. So before I get into that, I just want to consider this case here shown on the slide. Suppose we want to transfer power using three single-phase supplies as shown here on the left of this slide. And obviously, this system requires a total of 6 wires. And again, assuming all the supplies are identical, each wire needs to be the same size. However, as I'm going to show you in the next few slides, we can actually transmit the same amount of power using a 3-phase system using only 4 wires. And of course, by doing that, we're obviously going to save quite a bit of money in terms of the wiring. So as I mentioned just in the last slide, single-phase power transmission is actually not an efficient way to transmit power over long distances. So in general, we always use what's known as 3-phase power to do that. So what is 3-phase power? Well, it's shown here in the slide. You can see there's 3 waveforms, and they're all separated in phase by 120 degrees or 2 pi over 3 radians. And again, this is, of course, the ideal case. In reality, there's always going to be a little bit of maybe phase and magnitude mismatch. But I'll show you in the next couple slides that by doing this 3-phase transmission, it's got actually a lot of nice advantages and is a much better way to transmit power over long distances. What I'm going to show you in this slide is that we can show the sum of the voltages and currents in a 3-phase power system where all 3 phases are of equal amplitude and exactly 120 degrees apart, always add up to 0. So to do that, we make use of this trigonometric identity shown at the top of this slide. So again, what happens if I apply this to the second phase? And that basically works out to that the result is 1/2 sine omega t plus square root of 3 over 2 cosine omega t. And if I apply this identity to phase 3, you can see that the net result is minus 1/2 sine omega t minus the square root of 3 over 2 cosine omega t. So what happens then if I add these two together? Well, adding them together is just going to obviously give me minus sine omega t. So then if I take the sum of phase 2 and phase 3 and add that to phase 1, pretty obviously this gives me a net value of 0. Now, of course, in a real-world system, there's always going to be a little bit of mismatch, so that you don't always get the thing to sum exactly to 0. But in general, it's going to be very, very close. And this is again a very powerful and important property of three-phase waveform and three-phase power transmission. So if you think back to the slide I showed a couple of slides ago, where I was transmitting power using 3 different sources and had 6 wires. If we go to a three-phase system, of course, again, not only does it reduce the number of wires needed from 6 to 4, but you can see that reference or return path, which I've shown as a dashed line in this diagram, can be quite a bit smaller than the 3 main transmission lines, since it only has to handle current due to amplitude and phase mismatches in the three-phase system. So again, by going from single-phase to three-phase transmission, we've made a much more efficient way of transmitting power, and it's going to save a lot of money, because again, probably the most expensive part of any transmission system is again just the cost of the wiring. So reducing from 6 to 4 it makes a big difference in terms of power transmission cost, I should say. Now, the configuration I showed on the previous slide does have a name, and it's typically called the Y or star connection. I also want to point out that there's actually 2 separate voltages available here. So again, the voltage between any 2 of the phase lines is known as the line voltage, and the voltage between any phase line and the neutral line is known as the phase voltage. So, of course, a reasonable question to ask is, what's the relationship between these 2 voltages? So, suppose we have a phase voltage amplitude of 120 volts. Well, how do I calculate the line voltage? Basically, I just need to subtract one phase from another, and then determine what the amplitude difference is. So in this case, I've subtracted the second phase from the first phase, and again, using some trigonometric identities and solving for this, you can see that in the end result, there's a factor of the square root of 3 difference in the line voltage and phase voltage. So that means that the line voltage amplitude is given by 120 volts times the square root of 3, or 208. So again, this is, I think, pretty familiar to most people, 3-phase 208 systems, but that really comes about because there's 2 voltages available. Obviously, there's the voltage between any phase and neutral line, which is 120, and of course, between any 2 phases, you've got 208 volts. We talked a lot about the wire-star connection, and reality is that connection is taking advantage of the fact that, of course, the current sum to 0, but remember that the voltages on a 3-phase system also sum to 0. So again, if you just stack these up as shown here, you notice that the 2 points shown are actually both at 0. So if we want to, we can actually kind of just fold this over on itself, and this creates another configuration, which is known as the delta configuration. And again, this is taking advantage of the fact that the voltages in series sum to 0 volts. So this slide shows 3-phase power transmission in the delta configuration, and you might ask, well, how does the current flow work? Actually, this is not so hard to do. You can calculate the currents flowing to the various loads just by simply applying Kirchhoff's current law, which I've done here just for reference. And again, I've labeled the 3 nodes in the load with 1, 2, and 3. So hopefully everything is kind of clear how this is flowing. But again, it's fairly straightforward once you understand the basic concept that again you can configure these in a delta configuration, because again the voltages sum to 0 in series. So actually analyzing 3-phase power systems can be pretty difficult, almost impossible sometimes using a conventional oscilloscope, simply because sometimes of the power levels involved. So, of course, there are specialized instruments existing for this purpose. So I wanted to just mention, for example, Keysight has the PA2200 series of power analyzers, and the 2203 is in particular shown here. And this instrument has 4 channels, each capable of measuring voltage, current, and power. And again, I'm not going to go through all the bullet points shown on this slide. They're kind of for reference. But again, it's got a lot of nice capabilities. For example, you can look at real power, apparent power, reactive power, phase angle, power factor. You can analyze harmonics. It goes to very high voltages, currents, up to 1,000 volts RMS, 2,000 voltage peak to peak. So again, it's a nice tool if you need to do some analysis on a multi-phase power system. So this ends the section on power transmission. And again, the key things I'd like you to remember from this, of course, are that, again, the primary reason, as I said, that transmission is done using AC waveforms as opposed to DC is really due to transformers, the ease by which AC voltages can be stepped up or down using transformers. And again, because identical 3-phase sinusoidal waveforms sum to 0, it's much more economical to transmit power over long distances using 3-phase systems rather than single-phase systems. Next thing, of course, is simply that when you look at the Y or star configurations in delta, just keep in mind that the Y or star configuration is utilizing the fact that 3-phase current sum to 0, whereas the delta configuration is utilizing the fact that 3-phase voltages sum to 0. Lastly, I just want to mention 3-phase systems can obviously be very complex, and it's probably best to use an instrument specifically designed to test them if you actually need to verify performance parameters. Now we're going to get into section 4, which is power conversion, and this is actually quite a broad topic. I'm really kind of giving you in this section an overview because some of the areas that in power conversion we're actually going to cover in much greater detail in subsequent webinars, but this is at least a kind of a nice overview. So what are the types of power conversion? So in a very broad sense, I guess you could define power supplies as circuits that transform electrical input power, which is either AC or DC, into electrical output power, which can of course also be either AC or DC. And then this of course excludes things like power supplies based on rotating machine principles and power supplies that derive maybe electrical power from other forms like batteries, solar cells, etc. But again, based on these considerations, we can divide electric power supplies into the 4 kind of broad classifications shown here. And I'll go through just each one briefly. Like AC and AC out, that would be like line regulators, frequency changers. AC in, DC out, again, that really is what we normally call, or I think generally think of as a power supply, but that's going to be covered in detail in the next webinar in great detail. Also, we have DC out, which are like power inverters, and of course DC and DC out, which are DC to DC converters. So when we're dealing with AC to AC conversion, we're typically talking about either an AC source or an analyzer. So just to clarify, so an AC source is an instrument that can supply variable power and frequency to a load, obviously AC. And again, the reason you use this is to verify performance of AC powered equipment and check it for its kind of resistance or stability to events that might cause failure, such as surges, harmonics, grid interruptions, things like that. A lot of times AC sources also have a lot of measurement capabilities. They can measure DC or AC and DC superimposed. They can measure RMS values, real apparent and reactive power. Of course, I talked about those, peak voltage and current, harmonics. And typical applications include, testing maybe an uninterruptible power source, which is called UPS typically. Efficiency testing of DC supplies, AC power sources, looking at line disturbance, brownout testing of DC power supplies, AC sources, and things like efficiency and safety testing of transformers. So these are all kind of typical applications for these instruments. So as I mentioned a second ago, when you need to convert AC line voltage to a different AC voltage, you need to use an AC power source. I just want to point out here that Keysight offers 2 families of AC power sources. We have our AC 6800B series of basic AC sources, which are good. They provide very stable, reliable power, and we have models that go up to 4,000 volt amps. And we also have our 6800C series of performance AC sources. These provide a little bit more complete AC test solution because they've got things like built-in arbitrary waveform generation, which allows you, of course, to simulate different types of power waveforms. And they go up to levels of 1750 volt amps. And actually, both families can also produce DC power, either alone or as a DC offset to an AC waveform. So AC to DC conversion is actually, again, what I think most people think of when they think about a power supply. And that's really going to be the topic of our next webinar. So again, in this particular webinar, I'm not going to spend much time on it. I have a table here that kind of shows the different types. Again, there's two really main types of power supplies, which are linear and switching. And this table, which I'll cover actually in the next webinar as well, shows kind of some of the advantages, disadvantages of those supplies. And maybe in the next webinar too, I'll talk a little bit about even the history of power supplies, because I'm not sure everybody even understands that, because it's kind of interesting. I don't want to get into it now too much, but the power supplies originally were kind of created to eliminate the need to have the B batteries. Now, you ever wondered, why are there no B batteries? There's A and C and D cells. So there actually were B cell batteries in the 1920s that were used to power radios, and that was a cutting-edge technology in the 1920s. Radios, very popular. Everybody wanted to get a radio, and they used B batteries, but they were kind of heavy, and I think they were lead acid, and it was easy to mess up things or cause damage to your radio if you didn't connect it. So there were companies that started to get this idea that maybe they could sell power supplies that people could use in lieu of the B batteries. And of course, eventually the radio companies got wise and started integrating that into the radios themselves by the end of the 20s. But that was kind of the initial reason people used power supplies. Those were all linear supplies. And then the technology eventually evolved later on in the 50s to more advanced stuff. But anyway, I'll talk about that more in the next webinar. But again, there's two main types of power supplies, and we're going to cover this extensively in the next webinar. So let's take a second to talk about DC to AC conversion. The main use really of DC to AC power conversion is to convert DC voltage supplied by a battery into AC voltage. And of course, one application of this process, not necessarily the only one, is to supply power to an AC electric motor. And again, since virtually all electric vehicles use AC motors, again, this technology is pretty much essential to the modern electric vehicle industry. Now, a power inverter, which is sometimes just called an inverter, is a circuit or device that converts DC power into AC power. And again, the term inverter typically only applies to circuits and applications involved with power, where you have very large voltages and currents. Because in small signal applications, circuits that create AC signals from DC input are generally just known as oscillators. I do want to mention that the design of DC to AC circuits can be pretty complicated, and it's really beyond the scope of this webinar. But I can give you a couple simple examples that will kind of help explain some of the concepts used in these circuits. So again, one of the most fundamental conceptual designs for a DC to AC converter uses a transformer with a center tap on the primary inputs. And you can see here, by rapidly alternating the DC current between the two primary coils using a very fast switch, you can create an AC current in the secondary coil. But of course, implementing this switch in this example at the circuit level actually requires very fast switching transistors, as shown in the bottom figure here. So since power semiconductors, I should say, are such an important part of the DC to AC converter circuits, it's really important to understand power loss on these devices. It's crucial to their operation and characterization. And as the slide shows, power loss has three components. There's conduction loss, switching loss, and driving loss. So again, conduction loss is due to the on resistance of the transistor. Switching loss is due to the transistor capacitances and gate resistance. And driving loss is due to the gate charge requirements of the transistor. And again, I'm not going to spend any more time on this right now, because we're going to actually have an entire webinar devoted to this topic later on. So one area I want to spend a little bit of time on in this presentation is DC to DC conversion. So DC to DC converters take a DC input voltage and, obviously convert it to another DC voltage. But of course, almost all modern battery-powered devices of any complexity, employ one or more DC to DC converter circuits because they have to reduce the voltage of the battery down to a level appropriate for the different internal circuits. And of course, there are applications such as high voltage DC power transmission that also use DC to DC converters. But again, the key point of a DC to DC converter circuit really is that its output needs to act just like a battery, in the sense that it needs to maintain a stable output voltage regardless of the current loading. And again, I can't really teach you circuit design in this webinar. It's worthwhile maybe to understand some of the fundamentals of how DC to DC converters work before moving on to the subject that I'm going to cover really more, which is testing them. And actually, the thing is, DC to DC converters actually are sort of designed similarly to the way that linear and switching techniques are employed in AC to DC power supplies. There are DC to DC converters, for example, that employ linear voltage regulation techniques. They have some advantages in terms of like simplicity, low drift, minimal RF emissions, but like switching power supplies, they have some disadvantages in terms of they're kind of inefficient and they dissipate a lot of excess heat. So most modern DC to DC converters actually use some sort of switching technique similar to switching power supply techniques. And again, switch mode DC to DC converters basically work by converting their input voltage into an alternative energy form of some sort, and then converting energy back out into another voltage level. This is sometimes done magnetically with transformers or inductors, or electrically using capacitors. And again, switch mode DC to DC converters, honestly speaking, they're really complex circuits. They require a lot of careful design to ensure stability and minimal noise. But good news is, I guess, that today they're pretty widely available as integrated circuits, and they offer really great performance. So in the next few slides, we're going to explore some ways to verify that performance. Now we're going to talk about DC to DC converter testing. And again, the following are the most common, probably DC to DC converter performance metrics and test. First one is efficiency, which is the ratio of output power to input power. A second would be probably load regulation, which measures output stability under varying output loads. Like, in other words, as the current, say, draw of the powered device or devices changes, does the DC to DC converter's output remain stable? Third, you have line regulation, basically looking at output stability under varying input voltage. Again, this parameter relates to how stable the output voltage is as the input voltage is varied under constant load conditions. And then lastly, the time-based response of the output to sudden changes in output load. Again, essentially, this test looks to see if the output shows any glitches if you change the output load abruptly. So what are the requirements for DC to DC converter testing? So again, kind of regardless of the size of the converter, you obviously need a DC source to provide input power to the converter under constant voltage, and you need an electronic load to draw power from the output, again, usually under constant current loading. And you need to sweep the load current from 0 to the full load current capability of the DC to DC converter while being able to record input power, input voltage times input current, and of course output power, output voltage times output current. So I want to point out that if you want to test DC to DC converters in your bench, and also the tool that I actually used to make the measurements I'm going to show you in the following slides was the N6705 DC power analyzer. It's a great tool for this kind of thing. It's got 4 slots. You can put different modules in it. We've got many different modules. For the test I'm going to show you, I actually used a source measure unit to supply power to the DC to DC converter and an electronic load as the load on the other side of the DC to DC converter. But again, it's nice because this the N6705 eliminates the need for having different pieces of equipment, and everything is integrated. We can also use this instrument with Pathwave bench view, control and analysis software, so that you can do a lot of automation, and then it's also controllable over various GPIB, USB LAN, things like that. So again, for this type of analysis, it's a great tool, and I think I'll show you in the subsequent slides how easy it makes DC to DC converter evaluation. So typically, the most important DC test for the DC to DC converter is efficiency. And again, this is especially true for, of course, battery-powered devices, again, because efficiency has a direct impact on the life of a device. So again, the efficiency of the converter is the ratio between the output power and the input power. So you can actually easily perform this test using the N6705 power analyzer and BenchView software. And so in this example, we actually have I've stepped the input voltage from 8 volts to 20 volts while using an E-load to draw 100 milliamps from the DC to DC converter output. And what I've done is I've used the formula capabilities of the software to calculate the output power divided by input power, and then multiplied it by 100, of course, to display the efficiency as the input voltage changes, the red line at the bottom. So the markers show that the efficiency in this case changes from 81.5% at 8 volts to 67.4% at 20 volts. The load regulation test measures the ability of the DC to DC converter to sustain its specified voltage output when the load current varies at constant input voltage. So to execute this test, after powering up the product, you want to slowly vary the output load between the specified minimum and maximum current values. And again, the measured output voltage changes should be within the range specified in the product's technical specification. Of course, this test setup uses the same connections employed for the efficiency test that I just showed you. And the screenshot on this slide shows the output of a 3.3 volt DC to DC converter with 15 volts applied to the input as the output load varies from 100 milliamps to 500 milliamps. The line regulation test represents the ability of the DC to DC converter to sustain the specified output voltage while the input voltage varies within a specified range of voltages. So to carry out this test, you want to set the input power source to a value within the input range of the product and power up the product. So again, while monitoring the product output voltage, you want to slowly vary the input voltage between the specified minimum and maximum values. And the measured output voltage changes should be within the range specified in the product's technical specification. So again, the screenshot on this slide shows the output of a 3.3 volt DC to DC converter with a constant 100 milliamp load as the input voltage sweeps from 8 volts to 20 volts. So that concludes the power conversion portion of the webinar. And here the key takeaways that I want you to remember are that, again, there's 4 main types of power conversion: AC to AC, DC to AC, AC to DC, and DC to DC. Each power conversion type is actually quite complicated, and then for a lot of these ones, we're going to actually devote much more time in future webinars to covering them and talking about them. But the DC to AC power conversion I just mentioned has, of course, become especially important recently with the dramatic increase in electric vehicles, again, which virtually all operate on AC motors. So that's a pretty hot area right now. And again, DC to DC power conversion is, again, used extensively in all handheld electronic devices, really being driven by the massive explosion in the IoT device realm. This now brings us to the last section, where I'm going to give you a brief summary of what I covered today, and also give you some additional resources if you'd like to get more information on the topics I covered. So if I were to summarize this entire webinar to a few key bullet points, these are the ones that I would probably want you to take away. Again, the first one is that RMS gives us a convenient means to think about periodic sinusoidal voltages and currents, that is, by converting them into their equivalent DC values. The second one would be that voltamps represent the total amount of power a circuit needs to function, but watts represent the actual power consumed or dissipated by that circuit. The next point would, of course, be that three-phase AC power systems are the most efficient means to transmit power over long distances. And then lastly, just keep in mind that there's 4 main types of power conversion. They're listed here. And then, of course, we're going to actually talk about them in greater detail in subsequent webinars. I also wanted to make you aware I have a power handbook available. It's 146 pages. You can see here it's a table of contents, all the different chapters, everything it covers. So basically, all the stuff I talked about today is covered in this handbook, and of course, a lot more. It's kind of the general outline we're going to follow to some extent for the webinar series. Not exactly true, but again, most of the material that we're talking about in the webinars is also in the handbook. And you can actually download this for free. It's going to be in the resource listing shown on your console, or you can also get it by using the URL shown in this slide. But again, if you want to learn more about power in general, power products, any of the stuff I talked about, I highly recommend you download the handbook.